So it's my privilege to introduce our three speakers. Dr. Don Nielson, who was director of the Telecommunications Sciences Center and VP of the Computer Science and Technology Division at SRI International. He oversaw the packet radio program and many other programs of high impact for the entire world. And rumor has it that there was nothing that Don Nielson could do wrong at SRI, but I know better. He did one thing wrong. He dared to hire me at SRI when I was there. So, but rumor has it that he was one of the best bosses you could ever have, and that is true. And next we will hear from Dr. James Freebersyser, who is Director of Advanced Systems at Raytheon BBN Technologies. And I have also the privilege of knowing Jim from Packet Radio Times, global programs, and I forget now, one too many meetings, sponsored by DARPA and others. And last but by no means least is Professor Fouad Tobagi from Stanford University, who all of us know for his seminal work on CSMA. So without further ado, I'll give the floor to our first speaker, Dr. Don Nielson.
Thanks, JJ. First, a couple of observations. I hope this is funny. When I listened to, in fact, Luigi, when he had his long list of different derivatives of the Aloha system, I thought when you're there first, it's really important to attach your name to something. It's just like everything tissue you pick up as a Kleenex. Well, every random access protocol you pick up is Aloha somehow in it. It's either slotted or disciplined or whatever. It just seems to have a life of its own, and it goes on. The other thing I'd like to do is those people who are associated with the packet radio program, would you please raise your hand? Quite a few. The door is right over there if you'd like to leave, because I want to proceed with no... I can speak freely? Around you, Bob, I know that's dangerous. Okay, packet radio program, I'm looking at it for a decade. It had derivatives that went on longer than that, but I'm not addressing that. The participants, I had on the original slide, it was a big deal. And then I spread it out so it's something a little more exquisite. But the participants are as follows, and I put DARPA up front for more than one reason, because not only were they the purveyor of making all this happen, but they had enormous input to it, technically and otherwise. And Vince's not here at the moment, but Bob did, and I can't tell you how much their influence, they influenced the procedure, the progress of the program. SRI was the technical director of it, integrator, and Collins and BBN, and I'll come to those roles in a minute. These two participants really were theoretical. They were to do network analysis, theoretically, and they could never keep up, essentially. The force of the program and timing meant that the complexity of making mathematical models of what we were doing, the intricacy of it, really never let them influence us very much. I don't mean that pejoratively. It was just a very difficult time. Okay, I press forward. There it is. Now this is from 1987, so this is after it's over, but I wanted to use this to indicate to you the extent to which the packet radio program had some sort of connectivity. And this could be, we'll talk about the van in a moment, because that has maybe the only last kickable evidence of that program existing. This should be called the station because it's an internal one. It doesn't have to have any interface thing. And BBN was the builder of the station, which was the controlling node in the early days. Actually through it, there got to be multiple stations as we distributed the protocols. And the rest of them you can see are the networks of the day that emerged while the program was going on. But you can see really fairly clearly here an internet, the influence of the internet. SRI had responsibility for making these NIUs, network interface units, the gateway at least in our world, came out of BBN as well. And the very first gateway that I'm aware of came between the Packet Radio Network and the ARPANET, and Ginny Strazar at BBN did that. So this is kind of, since this is Aloha, you're going to get a tsunami, 2 or 3 slides full of stuff, and I'll try to pick from them so you don't have to. My audio channel may jam your visual channel here for a bit. So Bob already talked about the gaining the frequency. It turned out to be at L-band, and so think line of sight. And that had its consequences, of course, when you build a robust network, as opposed to something that goes over hill and dale and you have connectivity more easily obtained. We had to coexist with other worlds, and Bob's already gone to that, so I won't, but the SF radar thing he mentioned earlier in the day, when we had to check compatibility against the local air traffic control radars. And we had coexistence among users, and among users of the Packet Radio Network. So spread spectrum was there for a number of reasons, multipath measurements and coexistence. I put CDMA up here, and Bob's right, we only had one code. That was more of a hardware constraint than anything, but I think all of us thought we're going to, instead of TDMA or FDMA, we were going to the CDMA world, and we'll eventually explore the notion of where multiple codes could be used. I mean, that was that notion of sharing. As I mentioned, we had some interfaces that we had to meet. The ARPANET and the Ethernet existed at that time, but we made those interfaces work. Conventional military systems, not so much. That turned out to be really a hard problem. And so the acceptance by other people, the handoff issue went on for a long time, and I'm not sure ever quite made it other than symbolically. But that whole military communications infrastructure was not easy to influence. Some other things. Error-free operation in a difficult dynamic environment. That's an oxymoron to most people. Here we had to deliver stuff that was error-free, but you go under a tunnel, you go behind a building, you go through forests, everything happens that's inimical to error-free communication. So that was a big challenge. Maybe that was sort of up the top of the list. We wanted a network that performed well and flexibly and dynamically, but getting error-free. I remember there was one thing we would do, and we get the van you'll see later, but we give people these demonstrations, and early on, and this is the packet radio protocols, this is not internet or end-to-end TCP, we'd pull out a synthesizer card and the radio would stop. And we had this display full of numbers, 0 through 9, over and over, a perfectly easily detectable error picture. Anyway, we'd pull it out, push it back in, everything would stop, push it back in, we wouldn't see an error at all. I don't think I ever saw an error. And that was sort of the guts of, or the proof perhaps, the fact that that was something we managed pretty well. Area coverage, complete if possible. I'll get back to that in a minute. I've already mentioned, I didn't mention noise, but we had multipath problems and noise problems. And later versions of packet radio, the one I'm talking about, had 4 error correction. Most all of the error corrections we had was retransmission in the time, both inside the network and beyond. There was this question about what does the network do and what do the hosts do, and that was not unfamiliar in the ARPANET days, but we had the same issue in packet radio. This particular environment for this network was going to be much, much more difficult than a wired network. We had all these vagaries we had to deal with. And so the question is, what did the network handle versus what does the host handle? Well, maybe that's pretty obvious at the end, but we pushed everything into the network that we possibly could, with the exception of the guaranteed end-to-end transmission in case the packet radio network couldn't, at that point, deliver anything. We were resilient to loss of nodes. We had, as I mentioned, a centralized station, but we could also operate completely distributed. Bob had the notion, I don't know if he remembers, but tossing all these things in a box and having them self-organize. And they did. We got the radios to that point where they would self-organize. How they did it, I don't have time to tell you, but essentially announced to the rest of their neighbors that they were there, and we had what were called tier tables that went out from each particular packet radio to find out what the connectivity of the network was from each individual node. We also did, I think, really innovative things, like we could debug any packet radio from any other node in the network, and those were special tools we built. And believe it or not, there was an ability, if one packet radio lost its brains, an adjacent could actually reload it. I mean, that's a big network load, but the capability was there in order for that to happen. So resilience went clear down to the software reestablishment level, pretty complete. So network operation was transparent to the host, and the network information unit, not much different than the ones they talked about in the Aloha program, wound up housing the end-to-end protocol and in the interfaces as well. Efficiency. Just a word about it. When you get in this kind of a ratty environment and you're retransmitting all the time and you're trying to maintain a network under seemingly difficult conditions, it's not unlike Aloha, 1/2E or whatever. How much can you waste and yet maintain a useful service? So the packet itself, the packet radio packet, was like 2 kilobits long. We used about 10% of that with header and cyclic redundancy checks that were error detectors and things like that. So that was pretty efficient. But then when you look inside the network, I'll show you, well, look at that last line. Those are just some of the kinds of packets that the network used in order to maintain itself, to establish and maintain itself. I'll come back to the drop one in a minute because it's kind of fun thing. But this is just a partial list of all the packets that were needed in order to make things work. So there's an inefficiency there. Actually, there's necessary inefficiency. But I didn't want you to miss the point that this is just 2 end users sharing a single channel without a lot of overhead. The protocol structure, again, there's protocols all over the place, but within the network itself, we had to have a reliable protocol. It was called Channel Access Protocol, which handled all the network, packet radio network internal stuff. And it was a reliable protocol. You have to have a reliable protocol if you're going to control the network. You can't have lost packets and things. And so reliable means I will keep retransmitting until the destination gets it correctly. As I mentioned, we had cross-net debugging and software maintenance. Layering. Layering was an important thing. The ARPANET had kind of sifted that world out a bit, and CCITT world, the ISA world was at it, but we knew it was critical in our case as well, so we had a regular set of like 3 layers inside the packet radio network. For multiple access, it all came down to CSMA, Carry Sense Multiple Access. Actually, there was an allowance for Aloha and something called Disciplined Aloha, which I don't remember we ever used, to tell you the truth. It was in the radios and capable of doing it, but the Disciplined Aloha was sort of the difference is the channel have anything at all, or has a packet been captured? In other words, a useful use of it rather than an unuseful use of it. So a lot of stuff came. I mentioned that theory had a hard time influencing us, with the possible exception of multiple access. This was a hands-on, first of its kind world, and it was not easy to anticipate all the procedures and protocols and even hardware that were needed to make this system work work well. And so hands-on, I'll give you an example of that in a second. It has to do with that drop packet. EPR is the Experimental Packet Radio Network, used, as I mentioned, Channel Access Protocol. We also had to take, because this was a new world, we take tons of different kinds of measurements. It had to do with how did a packet make its way through the network and or not, and what was the reason that it failed. The whole questions of alt routing and multipath, all that had to be laid out in some sort of measurements to know how we could intelligently compensate for it. Again, I repeat, this isn't Aloha. This is a mobile, ratty, difficult, resilient network that, as you might guess, had the military application in mind. It had to work under difficult circumstances. And so we had to make measurements in order to intelligently make that happen. I've already mentioned that. All segments could be mobile. Even the station in certain Army applications eventually was mobile. And I'll show you a picture, 10 minutes. Oh, well, I got to get going because the good stuff is yet to come. Things we didn't get to, network security, power control. I thought we had more time because we ate lunch earlier. We didn't get to network security. Power control we didn't use, that was important. Directional antennas we never got to. Multi-destination routing came up this morning, didn't. CDMA, we never got to that. And selectable grade of service in terms of speed, priority, error tolerance, and things like that, we never really got to that. But we did get a lot. Demos. Boy, I wish Vitt was here, because he and Bob drove us crazy with demos. And I'm going to give you some evidence of that. But first, here's the drop packet. This is one you wouldn't expect. So you're tooling down the road in this mobile van, you have a connection to a computer somewhere else in the world, and all of a sudden it's gone. The connection is gone. You had a route which was initiated by the station, but all of a sudden you've lost your connection to the station and nobody can hear you that can help along that route. So here comes a distress repeater on packet, and it goes out. And anybody that hears it goes to the station and uses that route. The station then uses that route to get back to reestablish a valid route quickly. And so, as it said here, April 77, we could connect to an operating host from a terminal in the SRI mobile van while driving all the way from San Francisco to San Jose on 101. That may not seem like a lot to you, but we had repeaters around the Bay Area, which you'll see in a minute. I can't take time with this, I guess I'm out of time, but what I wanted to show you was the demos that we had to run. These are not small people. Director Heilmeyer, Colonel Russell was head of IPTO at the time, demo for other people, demo. These were all in 77, got really heavy. And even for the TCP working group, Army Science Advisory Board, 28 DOD representatives. I mean, you didn't just call out the low stuff, it was all the high stuff, and it was important for selling the program. And oh, was it? Well, I forgive you then. This is one example. General Starry was head of a big part of I can't remember, he was 3-star general. Heilmeyer, head of ARPA, all these people would come and get to ride around in this van, which we'll get to in a second. And November 77, a briefing for somebody, a Marine. This one on the top was one I'll come to in a minute, because this is the first 3 network packet demonstration. So a lot of people say, well, that's really the beginning of internet working, if not the internet. Somewhere in December of 1977, Frank Quo came to town and he got a demonstration. Okay, this is a picture of Vitt running things. This is Colonel Russell, who was head of IPTO at the time. And it's just, oh, here he is. I was just blaming you for everything. There was nothing that happened.
Sorry, I was doing an interview.
Oh, well, you're excused.
Well, I thought we were going to start at 2. Did we decide to start early? We moved up. Okay.
Okay. Subtract that from my time left. Okay. Here's some pictures I want to show you. And the van, I have to say, is the last vestige, I think, of any hardware in the program, and if I have some time, the cache of a beer garden. This is what the network looked like in the Bay Area. There was actually more stations than that. There was one at Xerox Park, and there was other places that are not on the map. But essentially, that's the high-level repeater access system in the Bay Area that operated for a decade or so.
Hey, where's Tam on that picture?
Who?
Mount Tamalpais. That's on that picture.
It's way up there north, but that was an interference test. We had no repeater
We
there.
didn't actually put a repeater.
No.
Okay.
That was Bob's interference test. Yes, right. Okay. So this is the first time TCP we'd crammed into an LSI-11, a small microcomputer. And Jim Mathis at SRI had done that. Oh, by the way, I forgot to acknowledge Ron, because we had this notion, instead of R&D, we were doing D&R, right? Demo and recovery.
That's right. Yes.
That's a Kunzelman input. Anyway, so this is the first time we actually used TCP. I think it's maybe the first time TCP ever went between two dissimilar networks, the Packet Radio Network and the ARPANET. And this particular place in Portola Valley is the beer garden, which we may or may not get to. The station gateway was built by BBN, and so that was in August of '76. This is the diagram which I think most people say maybe this was the beginning of internet working. We have to be careful between a small I and a large I. The internet is this big. But internet working, the things on which the internet works, this is probably as good a point of recognition as any, because we now had a satellite network, and as well as a packet radio network and the ARPANET. And so the van made a connection to ISI, a hosted ISI, down in Los Angeles by way of London. It was a kind of 5 logical networks and 3 real networks. It was kind of a big deal, but it was just one more demonstration which we had to dig out from the archives to even raise as this stuff started to become important. I don't think Bob and Vic know about this much, but Earl does. We had a project with the Navy. It's called MetaNet. And what I wanted to mention here was, you notice over there in the packet radio network, there's an airplane, there's a boat, and there's a van. The van was up on top of Mount Umunhum. For those who are local, it's the one with the big concrete block up on top. SRI had an airplane which was flying out over Monterey Bay, and an SRI's Acania vessel was out in sea. So we had a packet radio network with 3 different kinds of modes of operating that went through the ARPANET, through the packet satellite network to Malvern in England. And this also was the basis for a voice conversation. I think this is 1981, roughly 1981. But there were 2 satellite networks. One was called the wideband satellite network, which was built, speech research people used that a lot, and as well as the packet satellite that you already saw. So that's kind of a big deal in terms of internetworking. For a voice channel back in 1981, voice over IP, thank you very much. And I didn't think you guys were familiar with it. Okay, some pictures. Keith Kalimba, that's Keith. That's a packet radio station. The packet radio just above his head was the first one issued, and it was all in one box. Then it came in 2 different boxes, and there's 2 different packet radios in the station. Before we got done, SRI built this mini packet radio station. They were showing earlier about how things compressed. We went from 3 racks, 2 racks, down to one thing plus a memory box. And that was over, I don't know, 6, 7 years, something like that. That cart on the end is the one that Vit could hear in his hearing aids when he was in a conference room. The one down far end, the terminal, that was the packet radio terminal for conference room. This is the one on the Acania at sea at Monterey Bay. And here's the van, which I guess is now called the Internet van. Is that right, Mark? Well,
call it the van where the internet was born.
that's too long, but anyway, whatever.
It's called the packet radio van.
Yeah, it's a packet radio van. Anyway, this is what was inside of it. Not much. There was a dumb terminal up there, right there. That's just a data media terminal. That's the LSI-11 that held the end-to-end protocols, and these are 2 radios, one for backup. Driving around the freeways, doing whatever. We had a helicopter at one point. We did all kinds of tests for this, and the helicopter could really move, and that was a little bit of a challenge to us for speed. This is packet speech in 1978, and this is Jan Edel, and it could be Earl Craighill, but I picked the wrong one. We used a Mickey Mouse phone to prove that it was just, I'll make it, that it was just an ordinary telephone. You didn't have to have special stuff. Of course, the speech packetizer was sitting right there. That had to change the output of the Mickey Mouse phone into packets for movement in the network.
I think we're really lucky that that didn't get out into the news somewhere, so somebody would holler at us for funding a Mickey Mouse
project. It's okay now, though. Freedom of information, it's okay. We housed the packet radio in, oh, come on, Don. In a case, and actually went to the Army, and I just got it for a second. I talked to Mike Frankel, who ran most of the Army projects, but there must have been 20 projects, demonstrations in the military that we made that had an important influence because it made the people in the military see the potential of what was here. They could be mobile, and they could still be reliable, and they could get network access to those big, expensive computers no matter where they were. And the Army, Heidelberg, Fort Sill, Alaska, all over the place. Strategic Air Command. There was an airborne command post, which is where SAC went in times of difficulty. Well, we got a packet radio aboard that. And for relocation, in case Omaha got bombed, here was the packet radio network, and believe it or not, before that happened, they were hand updating databases between the airborne command post and SAC headquarters. And SRI came along with another application. No, you can sync these databases, and what happened in an hour or half an hour now went in seconds. So, big deal. Some of the times we had to build those applications and make it obvious to them. So here's the van. The guys are crawling all over because they're measuring it. You'll see why in a minute. This is in the Computer History Museum at the moment. That van there costs more than the original van to build, but it's a precise model of it, and the van itself is out back. I wanted to mention this. This is an SRI packet radio for the Aloha net. And this went there in 1974, before we got any packet radios from Collins. The notion was that Alan Okanaka was going to be at his repeater site on Haleakala, and we were going down into the crater, and we were going to come up like this and essentially access someplace at ARPA on the ARPANET. Well, Alan's repeater didn't work, so anyway, it went from the rim of Haleakala back to the ARPANET. Conclusions. It wasn't the simplest approach we could have taken. I think driven by Bob and Vint, which really took the high road. And as you saw, it was not it was technically complex thing to do. CDMA, surface wave devices, a resilient network. All that was pretty avant-garde. I have to admit that when time came for the handoff of packet radio, I don't think it was pretty instructive other than what could be done. When the cellular world went from analog to digital and then embraced the internet, then things really proceeded apace. And I don't know how much packet radio can take any credit for that other than the illumination of the fact that what could happen in a mobile, ratty, difficult environment for internet access. It was fun and was likely inevitable in some way or another. Now this is the beer garden. There's only a few left. Okay, this is Rosati's. This is the 1976 demonstration. And there's some of us there. That's the first what hath God wrought thing that comes out of the terminal. It's a packet radio, a weekly report submitted to ARPA. It went on and on and on. We gathered it from the other participants, and that was the first transmission, at least on TCP basis. And the wires went out past my Volkswagen to the van, and from the van up through a repeater into the gateway at SRI and into the ARPANET hosts back in BBN and at ISI. So I made that sketch. Up comes this detailed model of the van. This is overtraining. They built these models, and that's where there's a Mickey Mouse phone that's in it. So that's as important as anything. Okay, thank you.
So I'm Jim Freebersyser. I'm here really representing all the work BBN's done. I should say BBNN, because apparently from hearing some of the speakers talk, they always refer to it as BBNN. I always thought it was BBN. But I think we might have to change the name because we seem to be more successful as BBNN in some ways than BBN. So Aloha's been around for 50 years, and I have to say I've only been kind of active in the area for 25 years. I can still remember being in graduate school and driving the Aloha equations and just being impressed with just how neat they were, that you could go through all these kinds of gymnastics and end up with a very simple equation, and just how elegant the curves always looked. So it's kind of exciting to be here just to be part of this and to talk about some of the work that, that BBN's done over the years. If you're not familiar with BBN, it started out as an architectural acoustics company founded by Bolt, Baranek, and Newman, the grad student, who rumor is he did all the work, in 1948, and started out as an architectural acoustics company. And they moved on to using mainframe computers and then human-computer interfaces, then let's network the computers, and have moved on to, even since then, to things like speech and language translation, and more recently to synthetic biology. But for now, we're going to talk about some of the networking things that BBN's been involved with. And some of them you've already just heard about. That's a little bit of a relief for me because it's hard to talk about the first 25 years when you weren't there for the first 25 years. But you've heard about some of the things like the packet radio network. My understanding from talking to some of the people like Tony Michel and Jerry Birchfield, who were BBNers who were involved in those projects. There was, from a DARPA perspective, there was the original DARPA packet radio network. Then they moved on to the low-cost packet radio network. That was the name of the program, at least, that resulted in some of the things that were driving around in the van. And then after that was the survivable radio network. And in each case, there was always these incremental improvements that were going on. And then what really resulted in what I'll say the first practical military system was a system called the near-term digital radio. ITT built the radio, but BBN was doing the network inside. And this was a cluster-based system where a particular node would elect itself as a cluster head. The clusters would talk to each other, and then individual users would connect to one of the local clusters. So it looked like a very cellular architecture, except it was all very adaptive and very much on the move. One program that I think people are probably familiar with is a DARPA program called GLOMO, Global Mobile Information Systems. This was kind of, at least when I first arrived on the scene. And people like JJ were funded. I think Norm had a Spread Aloha program project that was funded as part of GLOMO. And I would say this is was kind of DARPA's last real researchy focused networking program that they had. And so if the first 25 years were very researchy, very experimental, I'd say the last 25 years, while there's still research involved, have been pretty focused on some of the, more focused on fielding things and trying to transition things to the military. I think because the electronics was getting mature enough to support packaging things into things that were practical for the military. But one of the things from a BBN perspective that came out of GLOMO was being able to use topology control to set up a network so that when you decided who was going to relay packets, to pick certain nodes to do that function, rather than just necessarily default to a nearest neighbor. And also something called the hazy-sided link state protocol, which rather than just flooding information to every node in the network, to the farthest edge of the network, you would update nodes that were, say, one hop away more often than updating nodes that were at the edge of the network. And then DARPA had another program called Onboard Switch that BBN was involved in, where we actually implemented an early version of mobile IP. If people remember mobile IP, Elizabeth is at least smiling. Mobile IP seemed like a good idea at the time. So two of the more earlier fielded systems for the military, BBN was involved with the mobile subscriber equipment program. This was an Army program that was really about doing voice on the battlefield. And BBN implemented a packet overlay network on top of the circuit switches in order to do data as well. And then we also were a sub to CDC for a Canadian program that actually put the data and the voice together going through the network at the same time. So I mentioned NTDR. NTDR was a program that the Army actually bought and actually fielded. It was in the first Iraq War in the early 1990s. ITT was the prime for that. And again, there were these kind of incremental improvements. JTRS was a joint military program called the Joint Tactical Radio System. And one of the earlier kind of experimental versions of that was a program called JTRS-2C. I'm trying to remember, I think A was like for aircraft and B was for dismounts and I think C was for vehicles, and I probably got that wrong. But that was a very similar system that was implemented with the CSMA MAC. And then we moved on to supporting Boeing, which was called Cluster 1, which was a vehicular-based system, again with a CSMA MAC. And what's interesting about JTRS-2C, it was really the first software-defined radio that was developed and fielded. Used a really ugly thing called Corba that people probably want to forget. And that's probably one of the reasons that, at least in addition to cost, that some of these systems were never really widely fielded, despite the long gestation times. Yeah, we need to check those dates. Yeah. Yeah, I'll make a note to check that and we'll update our slides. There was another program, there's at least a couple programs, as we're going through, I realized we missed. Jason Reddy and I, who helped put these slides together, completely whiffed on including the satellite extensions to Aloha. And then there was another program we should have listed here called, there's a DARPA program called Small Unit Operations Situational Awareness System that resulted in the soldier radio waveform that ITT eventually is still fielding that particular waveform to the Army. And again, that was based on a CSMA MAC. So earlier, the previous speaker mentioned some of the things that they didn't get to when they were doing packet radio networks, and one of them was directional antennas. And in the early 2000s, DARPA had a program called the Future Combat System Communications Program that did just that. You can see, looks very, very familiar with some of those antennas. There were omni antennas in the lower frequencies. There were directional antennas at 2.4, and then there were directional antennas at 38 gigahertz. And at the time, again, this is early 2000s, they were all switch beam systems. There was no phased arrays. But the point of those, the point of the system was to not just get the spectral reuse, but to get better low probability of intercept, low probability of detection and anti-jam by making sure if there's some particular person I'm sharing data with, it's only going to them. It's not going to everyone around me. And you could see some of the pictures there of the vehicles. We had roughly 20 SUVs, so we didn't have a really cool panel van. We just had rental SUVs that when we turned back in, they wondered why we'd had SUVs for months that only had like 1,000 miles on them. And they were very sandy for running them around at Lakehurst, New Jersey during the testing. But it was, from a Mac perspective, it was pretty challenging. I was the program manager at DARPA for this team. I was a DARPA program manager in the early 2000s. And there were actually two teams. One of them, BBN was doing the networking on. And there was a CSMA Mac that they were using for that they would do a request to SYN and clear to SYN on the Omni, then do the data and the YAC directionally. And then the other team, and BBN was working for TRW. The other team was actually led by Raytheon, who bought BBN roughly 10 years ago. And the main person doing the networking for the Raytheon team was JJ. So do you remember that? Just checking. So the Raytheon team was using a TDMA approach, but in order to dynamically and assign the slots to transmit and receive directionally on, at the beginning, there were slots within each frame to do those transmissions, but at the beginning of each frame, there were slots that were Aloha slots that they would say, this is what I have to send, this is who I want to send it to, and then there was a distributed algorithm that ran in order to make those kinds of decisions. No, this was out of ATO, which was a precursor of STO at the time. Yeah, the Advanced Technology Office eventually became the Strategic Technology Office. Yeah, when Tony came into DARPA, he changed the name of ATO back to STO because when he was a PM, there was a STO. Yeah, STO had gone away. So another program that DARPA had in the early 2000s basically said, well, if we have a MIMO physical layer, how does that change things at the Mac, especially at the Mac layer? Because at least at the processing of the time, it's kind of, everybody says, well, I have MIMO in my Wi-Fi router at home. What's the big deal about MIMO? But in the early 2000s, it was a pretty big deal. Even in those SUVs, they were pretty jammed full of electronics and even batteries, because the hardware we had to run it, the motor couldn't push enough power to charge everything. So they were using boat batteries in the back to help power all the electronics, and it was a processing challenge because the time needed to process a packet, because you could not start processing a MIMO packet till the last bit came in. The power needed the computational horsepower that you needed to chew on that packet. There was actually delays of several more packets were going to come in during that time frame. So trying to work out the MAC issues and the routing issues to make decisions before you had your packet was a challenge. And BBN had done this work with both, I guess it was Lucent at the time. I'm not sure what their name is now. They've gone through a couple of different iterations. But it was Bell Labs and Rockwell Collins doing the radios. Now, kind of going to the other end, BBN had a program with DARPA in the late 2000s looking at how to really crank down the amount of power that was used. And recognizing that a lot of the power that went into running sensor-type networks, which had very, very low, even lower than, lower utilization, even lower than just typing on a keyboard, at those kinds of utilizations, most of the power was going into just keeping the receiver alive, waiting for that next transmission. So we came up with some approaches that, again, were very Aloha-based for how to shut things down, how to know when to perk up and listen, and then go back into a sleep state to wait for the next packet. And how to do that while still maintaining, if you were going to go multi-hops, that packet wasn't just stuck somewhere in between the source and the destination for a long time. BBN has also done some, specifically some MAC and network protocols for EOD robots, electronic ordnance, or explosive ordnance, explosive ordnance disposal, where you don't want to get too close to something that might blow up, but because of the distances, you might have to string out multiple robots. And how can you close control loops to operate a robot when the video is not coming in? You need that video to be pretty close to real time in order to operate that robot and have it do what you want to do. So we did several experiments developing those protocols for different sponsors, including the Navy. Lastly, because there's just really no medium, whether it's air or water or land or in the air or under the ocean, BBN's also built ad hoc networks for mobile acoustic sensors, very small UUVs. A very challenging environment that really kind of throws you back to some of the data rates that were associated with the original packet network or even DARPA networks, where now you're down into kilobits or sub-kilobits kinds of data rates with very long propagation times over those distances. So how do you do that? Very, very critical to keep low overhead for those networks. This was a DARPA program that was called CNAV, which Vishal, do you remember I'm trying to remember the name, the acronym. Collaborative Network of Autonomous Vehicles. It was not classified. It was never classified, but it wasn't spoken about a lot either. Probably the most recent work we've done, and at some point, I'm not sure when, where packet radio networks became mobile ad hoc networks. I think it might have been somewhere around 2000 when the next generation felt like they had to rename things. But the wireless network after next program was probably our most recent large-scale foray into packet radio networks. A handheld radio, 4 channels. So you had to be able to manage those 4 channels across a pretty large band of frequencies. It would do dynamic spectrum access. So you didn't necessarily have to assign it frequencies. It would be able to sense interference, move away from that interference. It would assign those frequencies to the different nodes, to the different areas. You can see the coloration right there. And it also included disruption-tolerant networking techniques. So do I have 10 or do I have less than 10? Okay. He was. Yeah, he was the original PM for that program, and then Bruce Fetty finished it.
What is the number I think you should mention? The nodes were in over 100 real radios running.
Yeah, so that's always one of the challenges for these demonstrations when you want to get to scale. For example, the earlier Lakehurst demos, we had 20 SUVs that were driving around Lakehurst Naval Air Station because it was nice and flat with buildings and foliage and things that we could easily model and with bulk propagation in modeling and simulation and things like OpNet and QualNet. But here, for Winan, we had to take roughly 100 radios and make them mobile. So we had to hire people that we called radio walkers, and they had to, it's not the most exciting thing to do, but strap on a radio and walk in kind of prescribed ways, because if you want 100 mobile node network, you have to have 100 things to make them mobile, and at least at the time, maybe we're getting to the point where we can use robots to make things mobile, but at least at the time, you had to have either 100 people to walk them around or 100 people to drive them around. So that was always kind of a challenge when you want to scale a demo, because the people cost starts to kick in. So, some of the examples of these programs I went through, Aloha was in some way, it seems like it was embedded in every single one of them. Whether it was a true Aloha algorithm, or a CSMA algorithm, or a CSMA CA, or CSMA slotted, it seems like there was always one element that leveraged Aloha. And it might have taken, the first 25 years or so after the invention of Aloha till we saw, something like near-term digital radio that was a fielded product. But since then, as processing power has gotten, within the same form factor, the same cost, has gotten more powerful, we've been able to grow to, a lot of these other things that, frankly, listening to the previous brief, the stuff that's been done since then wasn't like it wasn't thought of at the time, things like directional antenna. It was just a matter of being able to get the processing power to do those. Now, we'd like to think that BBN has been involved in, a lot of these different programs. At one point, probably up until the mid-2000s, BBN had been involved in pretty much every packet radio network program at DARPA or fielded program, and it really wasn't until things like the IETF, Internet Engineering Task Force Man-A Working Group, took off that some of that technology started to flow. And Vishal Thapa is going to talk in a little bit in one of the sessions just about the things that BBN is still doing in this area.
Hi. Let's lighten it up a little bit. There's been so much done until today, since 1972, right? December 72, the first meeting for packet radio. And who am I to talk about packet radio after all these big speakers, those who led big programs and all these things? So maybe you would like to see things as it happened through my eyes in my journey, starting as a student. I was the small fish in a big pond, or I was in the presence of giants. For you to judge. As a matter of fact, maybe I did not do everything I could have to be that. I may bring that up a little bit in my talk. But what's important for me to sort of say is every person that has been mentioned, whether has been at the University of Aloha, working on the Aloha system or becoming inspired by it, having spent time there, or those who were at ARPA managing this program and leading it in a fantastic way, or at SRI, they all have influenced what I have done. So it's really a storytelling thing, and as viewed by me, okay? So it's very personal. Yeah.
You called it the University of Aloha.
Yeah, University of, yeah.
Yes. Is that a suggestion? Are you making a proposal?
Let me go through that story a little bit. How did it happen that I did whatever I have done? Would that be interesting? Okay, all right. And what role each one of you have played that I could mention, and I have a good list. Okay, so it's just storytelling, nothing more. But at the same time, I may be citing a series of papers I've worked on because I'm known for them or what have you. But not only my work necessarily. Okay, so I came to the US as an international student. Well, when I applied to come to graduate school, it was like 1969. I graduated from my school, engineering school in France in 1970. And how many universities in the US had computer science departments? Maybe not many. Stanford was only 4 years old, UCLA only 1 year old. And many other universities did not have it. So I went to the US Embassy in Paris, and like many of you have said, and I have said that many times before telling my story, before I heard it today, I could walk into the embassy, US Embassy in Paris without being checked or anything. And there was a library that you could go to. I'm not sure what it had, but there was one section that had to do with universities. And it's organized by departments, by fields, and I went to computer science. Okay, why computer science in France, or not teaching computer science? The last year of my engineering school, there was a specialization for 1 quarter, not the first quarter of the third year. That was economy and econometrics and finance, how to merge balance sheets when you merge company, because we needed to be educated sufficiently enough to be big managers, leaders in the industry. And in fact, there we learned nothing about everything. In other words, we covered so much from quantum mechanics and quantum physics to civil engineering, heat engineering, combustion engines, jet engines. I learned about how you could have an engine without a turbine as long as you could be launching it at a certain speed, then it can sustain itself by having just a Viterbi, I'm sorry, what is it called? A Ventura tube and fuel. Okay, anyway. So not to, I know at some point I'm gonna be shown so many, but it's okay. It's a story to be continued if it's not finished today. There is no goal, there is no conclusion at the end, except I'm still alive, active at Stanford, and I hope to continue doing things as much as I can. But I certainly teach, and I teach things about networks exactly the way they are presented here. I used to, like in an introduction on network course, I diverted a little bit. I used to sort of say the ISO model, here are the layers, let's cover each layer. And recently I realized that does not necessarily make as much sense as if I were to say how things happen. Therefore, from the very beginning, a little bit the telephone network, then moving on to packet switching, that's a paradigm shift. We are gonna do things in a different way and articulate why. And it came from Paul Baran, Davis, etc. And historians often like to know who coined the term, as if this is what's important. Not necessarily who had the concept, but did not say necessarily, utter the word packet. I won't say much more about that, but these are personal views that make me not. Anyway, so here I'm being a historian, but not by having interviewed people, by having seen things, experienced them myself. Okay. Anyway, so I went to this embassy and I looked at computer science, because that last specialization I had for the first year, the first time it was established, and it had to do with informatics. And there is numeric and non-numeric. Numeric means digital ICs, etc. Non-numeric, Markov chains, automata theories. I like that more because thinking I don't want to deal with circuits. Okay. And I'm sorry I'm giving this detail, and because for some of you, Professor Zadi from Berkeley was invited to visit, and we were only 6, 7 people listening to him. And he was talking about what? Database, data storage and retrieval as being a big thing at that time, 1969. In Paris. He was invited by the fellow who has established this little specialization. And the last quarter, actually, I did simulation of a computer architecture at INRIA, the Institute of Research in Informatics and Automatics. So the word informatics is still in my mind. A simulation of a computer model, and was very successful in a sense. Okay. So under the supervision of an American who was visiting there from Los Angeles. Anyway, so when I applied, I looked at those universities and ranked. So there was MIT, Stanford, and Berkeley, of course. Then Cornell and CMU, or I would say also, of course, but it was like a little. And I said, okay, I want to apply to these. But I said, well, you know, maybe 6. Let's add UCLA. It was the 6th. And before I left, I said, I want to add the 7th, Case Western Reserve University. And I waited, applied, I waited. Stanford, MIT, Berkeley, CMU, and Cornell all rejected me. Case Western Reserve University accepted me, and came the acceptance at UCLA. I looked at the map and said, Ohio, Cleveland, Ohio, Los Angeles, surf. Not windsurf, I mean, but surfing, etc. I'm going to go there, okay? I said to Case Western Reserve. And I was assigned to Cardenas, Professor Cardenas, who is still there at UCLA, who was in databases. All right, now, in those days, you would not go on the web to see who does what. This past week, I've been interviewing. I had 7 interviews with applicants, and we require that they tell us which areas they are interested in, what faculty members they would like to work with, and of course, they have to use the web for that. But at my time, I could not go see, there is Kleinrock, and there is ARPANET, etc. So therefore, I landed there, and met Mario, my good friend, late Mario, and Luigi at that time was there. See how many people I will point and I've known, okay, personally. And yes, I would like to work with Len Kleinrock. And I took his course. I chose his course, not knowing queuing theory. Well, it looked like what I was doing there in France. Anyway, that was a pivotal time. Len accepted me in December before even he saw my exam. But yeah, I mean, now we're talking about luck. Okay, so that's part of my story. Because when I tell people, I was lucky to have gone there to work on it. Okay, now, so, but first 2 years, you have to take lots of courses, take exams, and what have you. International student has to pay non-tuition, non-resident tuition fees. That made it like a private school for me. Not only the first year, but all the years that you are there. So it was not easy. And Len accepted me nevertheless. And I will give some details about that in person later on if you want. But be it that I am in that group. Second year, I did teaching assistantship because it paid the resident, but RA ships did not. And then he told me, now you gotta be with me. I said, sure. Pardon me? No, he doesn't. He doesn't. Yeah, that's right. But wonderful man to be with. I mean, I kept questioning. I didn't ask JJ. I mean, he is not present here, but he could be in my place, right? Anyway, UCLA has played a very important role in the ARPANET and later on in Packet Radio Network, or just to position things. It's the Network Measurement Center, and a lot of pioneering work was done in networking, given his past work in message switching and networks of that kind. You are right, and who are in important places as these computer science departments started getting formed in the nation. That's true. That's true. I can cite so many. Yeah, you are right. And some here, of course. Perfect. Thank you. Anyway. Of course. He was next door to me. I was always impressed by his work. Whatever I did, in my eyes, looked like nothing compared to his, by the way. He is very smart. Okay, anyway, we could say a lot of these things. But no, the point is, I have landed in the right place. I spent a summer at Yorktown Heights in Paul Green's group. So I got to know Paul Green. And then after, I don't know how, 2 months had passed and said, well, I should be showing something. I've not done anything. So I worked on variable load on a network, did some analysis of it and some simulation, say, here is my functional model, match simulation, or whatever. Paul Green offered me a job whenever I finish. Okay, but also puts me in a direction. This is the point I wanted to say, okay? I can always summarize everything. He said, what's important is the trade-off between computing and communication. There is some optimization. If you could work on this, it would be very good. Because they had already mini computers that could be connected to mainframes, large 361s or whatever, 370s, 360s, and you have to decide where you submit the job and is it locally done or you have to send it because very expensive to have communicated in order to reach another. That's not computer networking the way we see it today, but it was some form of it. Okay. And when back at UCLA, Len gave me the thesis of Dixon Dahl, some of you may know, who wrote it at University of Michigan, treating this problem exactly. So I read it. And then I come and I say, look, I see that he has solved all the problems I could think of, but I could do better analysis. He did like more engineering assessments and things like that. But I don't see anything novel, I told him. I said, I would be always having to cite that he has worked on this problem, but it is a more elegant solution. And, Len is not always very quickly convinced of that. So after 2 meetings, me having said the same story, I had to find a strategy to deal with this matter. And I said, he seems to like to be challenged. I said, all right, I'll tell you what. How about if you think of a problem that I should look at? If I show you it's in here, I don't do it. But if you find one that I don't find here in this thesis, I promise you I'll work on it. So he got challenged, so he started coming up with this or with that. I say, well, it's here, say it's there. And he says, that's okay, fine. That was towards the end of November or maybe early December. Then he called me one time and he said, I'm going to SRI for a meeting. You want to come with me? I said, sure. I have no idea what it is about. It was the very first meeting you were at, Bob. The very first packet radio meeting. As we entered the room, there's a fellow by the name of Brandon who came to greet us. Dave Brandon. And then, in fact, one thing I remember, he came towards me and says, Professor Kleinrock. I said, no, excuse me. I remember little stories that I'm giving you now, which are fun. I'm not going to talk about what packet radio is. You already know it, or Aloha, or whatever. But this is kind of useful. And, wow, I'm on a project. The first packet radio temporary note, remember there was a list of packet radio temporary notes that we were writing. And I had all of them until 1987, until finally clearing space, etc. I didn't want to throw them away. I was holding onto them. I gave them to UCLA. Now they are at the archive that Len Kleinrock has established. And they are accessible there. Which means I didn't have them to sort of see what is my very first packet radio temporary note that I have written. But given that in a packet radio network, you would not, in mobile nodes, you may not know where your destination is. You do flooding. Plus, even if the network did use a station to control packet radio units, given the limitation in each such unit in terms of storage and processing capability, very good paper in one of the special issue in the IEEE proceedings about packet communication networks, written by Bob, about advances in packet radio networks. Excellent paper. Excellent paper. You articulate things so well. Yeah, I'm sorry. Yes, that is the list of all. Ron Kunzelman was there too. Of course, Ron and Grandmeyer. Thank you. I'm saving time. I'm sorry. Maybe Bob et al. Okay. So I brought it here. I said, look, there is a reading list I'm going to give you. I'm not going to show you things here. It is a reading list. If you like, I can make copies. Yeah, exactly. Anyway, So just to be a little bit, to go a little faster, but that was the very first meeting. And since now you have had history of all these things that have happened, I went to all the packet radio network working group meetings until 1987. From when I was at UCLA, plus later on when I came to Stanford. Okay. Now, so that first contribution, I mean, I didn't think I have done anything. Well, you know, this selective flooding. Maybe you know where the station is, but you don't know what the route is. You flood in a directional way, or maybe you know that this is where that unit that you want to reach is. Why do you flood in all directions? Okay, when I looked at this later, I said, wow, that's kind of interesting. But anyway, so to continue a little bit my involvement in this, because there are key points that have happened, historical moments. I know that Norm is not here, but early in 1973, first meeting was December 72, but it was only organizational, and you wrote minutes of this meeting. That was very interesting. Objections. Either PRT1 or PRT2, PRT1 having been the convocation to that meeting, yes, but maybe PRT1, yes. And in fact, later on, when I talked about ad hoc networks and all these things, I always said, what was important about the work in packet radio and the fact that there were specific objectives to meet. Like you want to be able to accommodate data of this amount or voice also. After all, Paul Barand was for voice communication, but encrypted and resilient to attacks and all these things. Okay, so Norm came to a 1 minute left, and the rest is history. Norm came to a meeting that had to do with what Dave Wax told him when they use a repeater to go from one island to another, because they wanted to expand the range of that Aloha system. That repeater could not transmit if it is sensing, because that unit, contrary to the terminals and the computer, central computer system, would be having a transmitter and a receiver on the same channel. That was key. On the plane ride back, Len and I, we start saying, wow, that could be very interesting compared to everything that was done in Aloha. And we started working something. The first paper came out in June 1974 at ICC, but it had gone out before the name CSMA was created. And it was auto-slotted Aloha because it was the one persistent CSMA, which means that if you are blocked, you wait until the end of this transmission and then you transmit. Okay, later on, I involved PCSMA, probabilistic retransmission. So these are in the language of the scheme. So PCSMA, this becoming one CSMA. And let's see, because we are talking about that, I acknowledge Dick Bender, who was at Hawaii, and he had something like, even simpler. If you are not able to transmit, go away, reschedule to some later time. Called it non-persistent CSMA. But I've done lots of analysis that today I may not understand, but it was very useful because Bob Kahn, talking to the chairman of our department at one dinner, was Joe Goodman, and we had you to help us. Yes, he's the optics guy, Fourier optics and all that. And we had a little meeting because you were an advisor for our Center for Telecommunications, that you would come and talk to us, and you came from a meeting that had to do with artificial intelligence. And you were very frustrated. You have been putting millions and hundreds of millions of dollars in funding at that time in AI, and all you see, that's in your words, all you see is like always religious stands on some, but no evidence as to why one could be better than the other. And you cited my work, so you gave me a little boost because you said, No. Because you said, for example, you were complaining about the AI groups, how philosophical they were about their views, but no evidence that they should be followed as opposed. You pointed to them about my work, saying, here's Fouad, for example. He has studied, he had a scheme, times is up, he had a scheme, but then he did its analysis. and showed you the result, evidence, you were convinced you want to use that, the right selling point. So it's true. And that's what was specific about UCLA, where we were performing analysis and measurement center, but also we came up with the schemes, so I could study the schemes. Another interesting point I should mention is that since I was going to these working group meetings, one of them was held at Hawaii, okay? And I cannot tell you exactly the date, but I had already written a few temporary notes that had to do with CSMA. And you asked me if, Frank Cool, asked me if I would go to lunch. I said, sure. So we went out to lunch. Do you remember? Let me tell you what you did. You said, Fouad, very much interested in you. We're wondering if you would accept to join us as assistant professor. I said, but Frank, I'm still working on my thesis. It was actually chapter 2, I had 5. And I remember having spent time at the beach working on the next one that I was going to publish. So my answer was, I'm still working on my thesis, so maybe it's premature, but thank you for having made that offer. It was well received, but okay. So I continued, therefore, working until I kind of finished. In fact, there too, I could say at one time, because I've done here the series, part 1, part 2, part 3, part 4, with the reservations using Aloha or CSMA, so you reserve the channel, or the hidden node problems and the stability aspect, which I studied pretty well, following the footsteps of Simon Lamb. So all this was very good about CSMA. That was extremely important, okay. And he told me, I think you have enough. If Frank had thought that I had enough before, Len, several papers later, thought that also I had enough and I could write my thesis. Stupid me, I looked at him and I said, no, this is part 1, single hop. I still want to do part 2, multi-hop networking. The only final time that I finally understood what multi-hop networks are and how they should be studied is in the Wi-Fi context, given all the things that you could be doing at the physical layer, as pointed out in the paper issues in packet radio networks that we had written, Don Nielson, myself, and Barry Leiner. And that part was mostly mine, saying, yes, there is power control, data rate control, threshold for being blocked. Amazing how complicated the system is, okay, that only in 2010, with a student of mine, where it took a brute force approach, where we did simulation, et cetera, to realize that actually it's not because you have a link that can allow you to go like giant stepping, to go very far and reach the node. Maybe it's better in wireless network to go more in shorter steps with smaller blocking regions so that you have more spatial reuse. So it was a joint optimization of physical layer parameters adjustments and route selection, which links you would use in routing the packet in a multi-hop fashion that could give you the best capacity. It takes a while to finally understand that problem. Anyway, so.
Before you got your PhD, how many papers did you publish already before you got your PhD?
Well, all the PRTNs, of course, but they're not papers. Yeah. The first, let's put it this way. I'm glad you asked that question. There was just this conference paper in June, ICC, Minnesota, but it was not really the full thing, okay? It was directly a journal paper that we submitted before I had graduated, but appeared, it takes some time to go into the journal, but appeared in December 75. This is the paper that I received the test of time, Len and I, of course, my advisors, we received the Test of Time award in 2016 from SIGMOBIL. Okay, finally, it's recognized as that, but it's not. Because it was inaugural award, they went back as far as they could, and they needed to capture papers that had to do with mobile communications and wireless, therefore. Norms was the first, 1970. Lens and Minds was 1975. And after that was 91 and beyond. So that's where it was. Now, regarding the name, who came up with the name Carrier Sense Multiple Access? Norm, last time in 2007, he says, Fouad, you know, this Carrier Sense Multiple Access should have been called, I wish you were still here because I agree with him in a sense, should have been called Sensing Aloha, because then the word Aloha would have been there. But as a student, and then, okay, comes a visitor from RAND who said, I just visited Bob Metcalf. In fact, that first meeting where Norm Abramson talks about carrier sensing, Dave Wax having said that, happened to have been at this meeting. Then he disappeared because he was doing already Aloha for his altos on a coaxial cable, but he found out that he could do the carrier sensing too. He added the collision detection because it's on wire. You could be listening and transmitting at the same time. So I won't go through any detail more. So it became important for us to publish. So I go and see, I said, you know, this visitor just told us this. Then we need probably to publish, Professor Kleiner. We need to publish. But if we were to publish, we need to give it a name, the right name. So I was thinking Carrier Sense Multiple Access. I was reading papers, TDMA, FDMA, CDMA, and I said, that will be CSMA. He wanted something more catchy. You know, Aloha is a catchy name. Like what? Charisma, he tells me. I said, no, I like CSMA. And CSMA is on the title of Ethernet standard. Plus CSMA is in Wi-Fi, etc. So it was right to have done that. But certainly we do not want to do, that's an afterthought. I said, could it have been KTMA, Kleiner Tobagi multiple? How arrogant. Or TKMA, forget it. I always think things, yeah. I think
We'll take more questions after we thank our speakers. So if I may ask our three speakers to come to the front so that we can open the floor to questions from the audience. And so fire away. Oh, microphone.
Is this still on?
Yeah, that's still on.
This is still on? Yeah.
Well, you have to turn it on. Oh. It's on. Okay, questions?
Yeah, I could ask questions for both Don and Jim, but I'm going to ask one for Fouad. You have written an enormous number of papers in your career, very large number, mainly mathematical, all with different results. And you may think you've already addressed this, but I'm not sure whether you have or not. But of all the results you got, what are you most proud of? Or what's the most deep insight you've ever gotten into anything in the papers you've written? And if those are different, you know, what are the two different ones?
Well, of course, I've published in various applications areas, right, like multimedia, voice over IP, etc. But really, I would say CSMA, my first paper. After that, nothing better.
You mean the name?
No, the Carrier Sense Multiple Access paper.
What's the result in there that you're most proud of?
Oh, the result is, I mean, that's the point, is that we had 18%, like, Norm said, you get 18%, right? With slotted Aloha is 36%.
That was like 96%?
Well, 85.
I thought it was more than that.
No, well, it's very much dependent on the propagation time, because the vulnerable period of a packet that started getting transmitted and hasn't been seen, therefore, okay, so it's very much dependent on that. Plus, if the packet is of a certain size, the higher the data rate, the shorter it is, therefore the ratio gets to be larger. Okay, so understanding these things is very important, whether it's Ethernet or packet radio. The other is really having, because it was so much that I wanted to do, part two of my thesis. When I start realizing how much it was complicated to do that, I spent 6 months. In the end, my thesis could have been like maybe 18 months or less, including the writing, because I was writing as we go. Anyway, it's that paper that and make me understand a little bit better the Wi-Fi mesh network aspect with the multi-hop, including the routing, because it cannot dissociate the capacity of the network, which I struggled a lot to work on. Barry gave me some work to do and all these things. How do you define, how do you express, no matter what analysis you do, in simulation you do, was not very easy. Plus all the variability that exists in the system, many parameters to optimize. So the joint optimization of these two was the appropriate thing to do and gave me better understanding.
Thank you. Other questions? No? Oh, back there.
Hello, Benon Desfuli from Santa Clara University. So, hello?
Oh.
Hello? So my question is, how do you see the impact of CSMA for the future of communication, especially because nowadays most of telecommunication, protocols, standards are moving towards TDMA, as we can see, for example, 802.11ax. Includes a lot of TDMA-based mechanisms, right? Because they realize, that this significantly increases, performance, especially for mission-critical applications. So what do you see, as the future of CSMA for local networks, for cellular networks, or for wide area networks?
Because CDMA, you are spreading the signal, then it's almost like, it looks like noise, all right? Then it may be more energy detection. So CDMA, if the codes are not the same, they could coexist. The transmissions could be simultaneous and not hurt each other. Okay, so it becomes a matter of knowing how how many are transmitting. It's a energy sensing MA type, but it is what also could be referred to as CSMA. As a fact, in Wi-Fi, in some like the physical layer A or others, they say here are all the different modes of energy, CSMA, or carrier sensing, or energy detection, energy threshold, not necessarily having acquired a carrier. So that, just like the variants that exist in what do you do if you are not able to transmit, you are inhibited. There are so many variants. I say here are the many shades of CSMA, but it's the same principle. The hidden node terminal was very important. That was part 2, because if you're not able to hear, but you could be colliding at the destination with another transmitting station, that's worse. So you have to have a busy tone form. In the older days, at the time we were working, you could not have things dealt with packet transmission, with special control packets like RTS, CTS. You see it mentioned. You still see CSMA in the most recent systems. But you see also the RTS, CTS, which is what Wi-Fi introduced to make it collision avoidance, right? You send an RTS, you repeat the CTS, and the CTS can have a reservation. Says, whoever has requested to transmit to me wants this much, therefore stay off, all right? That was part 2 of my paper, but I did it with a split channel because Stan Fralick at SRI had come up with the idea that we will have different channels. At that time, I had to study it that way. But today, you do more things in having transmitted different control packets. Then, early on, it would be too expensive to deal with a packet just to make a reservation, unless it is worth doing, because you are interrupting the receiving station, having to do computations. And AppleTalk used RTS, CTS in order to do things in software rather than as in Ethernet to do it in hardware. The collision detection being inside the Apple II.
I'll pass the token to Don.
I have one thing that I felt kind of too rushed to get through everything, but there's one thing I wanted to mention that had to do with spread spectrum and multipath. It turns out when you're in a mobile environment, multipath can change its characteristics very, very quickly. And so when you think of a spread spectrum signal, you think I'm going to resolve the multipath and I'm going to match filters with that. But sometimes things are going so fast you can't keep a match filter consistent with what you see. So we had to wind up compromise doing post-detection integration. We never used the spread spectrum to resolve the multipath, darn it. And that would have come later with faster processors. But all through packet radio, I think we made a lot of compromises that weren't necessarily fun to make, but we had to prove the system worked. And so those were one of the compromises. Also, was there anybody in the SRI group that has a background story they want to tell? I felt like we didn't get it out well enough, but anybody from SRI, just quickly?
SRIers?
Okay, all right, thanks.
One more question.
Is Carl Auerbach still here? Or did he disappear? Okay, well, Carl raised the question about broadcast. And I wasn't too happy with any of the answers I thought I might have heard, if there were any. I still believe that we have not taken advantage of protocols that recognize that broadcast is a legitimate way of delivering information. Even if not everybody gets the broadcast, there are recovery mechanisms that you could imagine. Has anyone actually worked on taking advantage of the fact that multiple parties can receive the same information at the same time in order to make more efficient the distribution of content that's identical?
I might say that it was on the list, I don't know where you saw it, but one of the things we didn't get to was multi-destination routing. It was just too many things to do in too short a time, but it was something that would have been valuable, I think, efficient. Pardon? Yeah, it's still an opportunity. Yeah. The whole question in the internet of being able to adapt to the terminal which you are using in a way that makes it efficient is really still hanging out there, I think. And you have a lot of adaptation to do. When you pull this out of your pocket, it's a whole lot different than your desktop computer, and that's accommodated really well, but still a lot of world to go.